from a student who couldn't be here, so I want to answer that first, and then I'll open up to your questions. This is fall 22, the free response, which, by the way, is a good, I know I said fall 23 is good for your free response, but this one is very similar to, it'll look a lot like this, so it's another good one to practice. And the questions will mostly be the same, it's just the figures and the numbers will change. So in this one, number 3, the student asks, for the total momentum of the system, do you use the initial or the final in order to find that total momentum? And the answer is that, well, you could use either, because momentum is conserved, and so the momentum in the initial state is the same as the momentum in the final state. It's kind of like with the energy problems, that the energy is always the same, so you just have to equal one another. But in this case, of course, it's easier to look at which the initial or final to find the total momentum. The initial, because you just know everything about it. So I would find that total momentum, I would just say that the total momentum in the initial state is the mass, 1 kilogram, times 4 meters per second, plus 3 kilograms times 2 meters per second. And then just be careful my signs. They're both positive, so that's just 4 plus 6 is 10 kilogram meters per second. So that would be the answer. But once I find the velocity of this 3 kilogram mass, I can calculate the momentum of this final state. It would be the same, right? That 10 would be equal to 1 times 1 plus 3 times V2F. So that's 10. That's V2F is equal to 3 meters per second. And so then, of course, if I plug this back in for V2F, well, I would get, that would be equal to 10. So the total momentum is going to be the same always. It doesn't matter initial or final. But for you, you're going to know the initial speeds and their directions. You'll know the initial velocity, so you'll just consider the initial momentum will be the total. All right, I think that was the only question that I had that came in from other students. Do y'all have particular questions? Yeah, Allie?
Number 11 on
2018 exam 3. It's going back a ways, huh? What number?
11.
Number 11. Was there enough for your response on this one? Okay, you'll definitely have one that's similar to this. I don't know if it's potential energy or kinetic energy, but you'll have one where you have certain type of energy and then you convert it into elastic potential energy, or vice versa. We worked a couple variations of this. So do you want me to just work it, or do you have a specific question about it? Yeah, of course. So what's happening here is I drop this ball from some height and it falls down onto a spring. And when it falls down onto a spring, it compresses that spring. So it has potential energy here that's gravitational, and here it has elastic potential energy. Gravitational potential energy here, elastic potential energy here. So what I do is I set the gravitational potential energy, mgh, equal to 1/2 kx squared. And then I think I know everything. It's like h equals 10. I don't know k, right? Was that the problem that you encountered? That how do I do this if I don't know k? I talked about this in class, and you're going to see something similar on the exam. I'm glad you asked this question. That you know that F is equal to kx. So I tell you here that when I compress the spring by 2 meters, that's x. Oh wait, no, I'm sorry. No, I'm sorry. No, wrong question. There are a couple of different ways you could do this. So if I drop it from a height of 10 meters, it compresses it by 2 meters. Let's do it this way. Let's use these first numbers. If I drop it by 10 meters, it compresses the spring 2 meters. And then I want to know, what if I drop it from a height of 20 meters? By how much does it compress? Let's just go with the first one. I have m times G times 10 equals 1/2 of K times, no, that's not the right way. Let's look at it this way. You can probably tell since I haven't worked this problem in a while that it's probably not going to be on the exam, by the way. But let's just look at it. If I double H right here, well, how is that going to affect X? By how much does X have to change? Not 4. This is a little tricky. We haven't done one like this before. If I double X, that is that I have, or I'm sorry, I double H. Let me write it out. If I double this quantity, so I have a factor of 2 on the left-hand side, by what amount do I have to change X in order to also get a factor of 2 on this side? Not 2, is a root 2. Right. I have to root 2 this side in order to get the same factor of 2 on that side. So if I compressed it by 2 meters before, now I'm going to compress it by 2 meters times root 2. And so that's 2 times 1.4 or 2.8 meters. Let me just check the exam real quick. I'm pretty sure that I didn't put one like that on there. I worked through it last week, so it's been a bit. There was a couple spring problems, at least one. Yeah, not one on there like that. Okay. But good question, though. All right, you understand? Yeah. How? 22, 10, 11, and 12. All right, this one, the railroad car one? Yeah, so I have a railroad car, mass of 2,000 kilograms. It runs into a stationary railroad car with mass 6,000 kilograms. They connect and move at the same speed. Okay, so first of all, this is a perfectly inelastic collision. That means they stick together and they move at the same speed. So I have these two cars, and this one is traveling at 4 meters per second, and this one has a speed of 0. And this one is 2,000 kilograms, and then this one is 6,000 kilograms. And I want to know, after they stick together, and by the way, when they stick together, they're going to have a combined mass of 8,000 kilograms. What is their velocity going to be? All right, so let's just think about this. We'll work through it. But I have this object at 4 meters per second, and now all this momentum is going to go into this 8,000 kilogram object. That means that I'm going to be quadrupling the mass. So if I quadruple the mass, what has to happen to the velocity or the speed? It's going to go down by what factor? I went up by a factor of 4. It's going to go down by a factor of 4. So I know then that the answer, it was 4. Now it has to be 1. But we'll work that out. I say PI is equal to PF. That's 4 times 2,000 equals 8,000 times V final. And that V final is equal to 1. Okay? And then this one, I want to know what is the force. I have a mass equal to 3 kilograms. I have a change in velocity equal to 12 minus 8. That's equal to 4 meters per second. I just did the final minus the initial velocity to get that. And I know that the time is equal to 6 seconds. And so to find the force, I say, why is that doing it? To find the force, I say that force is equal to delta P over delta T. My delta P is mv delta V over delta T. That's going to be 3 times 4 over 6. That's 12 over 6. That's 2 newtons. You'll be able to identify these problems because it'll just be one object. You're not having 2 objects collide against one another. You just have one object with a force acting on it and a change in its velocity. Like in that momentum chapter, you have collisions, and then you have what we call impulse problems. And this is an impulse problem. I apply a force on an object, and it changes its momentum. This is also an impulse problem, number 12. It's a little more complicated because you have to be really careful about the sign of the velocity. So if you see a word like rebounds or goes in the opposite direction, it's really important that you get the signs correct. So here, VI is equal to 10 meters per second, but then V final is equal to 2 meters per second. But because it rebounded, that is, it bounced off of the wall or whatever it ran into, I know that this has to have the opposite the sign. It doesn't matter what sign they are, they just need to be opposite one another. So if I find delta V now, which I'll need, it'll be V final minus V initial. That's going to be -2 minus 10, which is equal to -12 meters per second. Anytime I have something that's bouncing or rebounding, the difference in the final and initial velocity will really be the sum, because I'm either going to have 2 negatives or I'm going to be taking the negative, I'm going to be subtracting a negative number. So if I want to find the force, it's just like I did before, m delta V over delta T. And then that's going to be the mass, which is 1,000, times delta V, which is -12, divided by delta T, which is 0.1. That's 12,000 over 0.1. That's 120,000. But notice the mistake, the common mistake here would be to find delta V is not 12, but the delta V is 8. Because you would just do 10 minus 2 or 2 minus 10. But that would not be correct. That would give you 80,000, which is an option, but it's not the right answer. Just be really careful. If you see something that bounces or rebounds, that when you take your change in velocity, beware that it's not going to come out. The difference is actually going to come out the sum of the 2 velocities, that I have a bigger change in velocity. All right, that was the whole point of the bean bag versus the rubber ball. When it hits you, then the rubber ball hurts more because it has a bigger change in velocity. The bean bag just hits you and then stops, but the rubber ball bounces off, and so it has a final velocity that's in the opposite direction. So delta V is bigger than it was. Did
I'm here because I need a review, so I hope you don't mind.
No, I'm fine. Momentum and energy. Okay. All right. Well, if you have questions, just let me know. All right. Colin, we good on those? All right. Those are all great questions, and you're going to see some like them tomorrow. Yeah, no? 15? Yeah, so this is, I just want to know the angular displacement. I often give questions that similar to this. The clock question is a similar one to this, right? You can divide this circle into pieces like that. Now I know that if the pi was this big, that would be pi over 2 radians, because 90 degrees is equal to pi over 2. That's just something y'all need to know. Like, you need to know your circle, okay? And so if that's pi over 2, then that means that this little piece of the pi, which is half of it, should be pi over 4. All right, so on your unit circle, remember 0, pi over 2, 90 degrees is pi over 2. What's this? Pi, 3 pi over 2, and then 2 pi. I'm pretty sure you have a question that just, requires that you need to know your unit circle in that way. I said the clock questions are similar to that. I don't think I want to did I tell you on the clock question? I don't think so. But I'm sure there'll be something like that. I think. All right. What else, y'all? Yeah, Emily.
5 and 6 on
Exam
exam 4.
4, 2020?
Yes.
Yeah, so just beware that you're looking at exams 4 too, okay? Because there are some questions on exam 4. And most of the questions are new, but as you've probably learned from my first couple of exams, I do reuse some past questions, so you'll probably find, I don't know, 5, 6 questions that are from past exams. Oh, they're out of order. Shoot. Is it very at the end? Fall 20, you said, right?
For me, it landed on slide, or page 51.
Okay, I got it right here. What number?
5 and 6.
5 and 6. Okay, this is a kinematics question. You have a specific question about it, or just work it?
My brain kind of just stops working at some point.
Why don't I just work it? Because you will have a kinematics question. The way I recommend you approach it is that you write down your equations if necessary. You might just know them, but I always find it helpful just to write them down. That way, when I look at the problem, I can just sort of reference them. Or you'll have your equation sheet, so you can just have it right there. By the way, the equation sheet will be a whole separate page. I mean, I know that killed about 100 sheets of paper, but we just pull it off, and then you can have it separate as you're working through your exam. So you'll have your exam, your bubble form, and your equation sheet as 3 separate things. Anyway, now we just write down the things that we know. A fan is switched on, so that means it was off prior. That means that omega naught, the initial velocity, is 0 radians per second. And then it reaches a speed of 240 radians per second. Oh, no, and then you turn it off, and it begins slowing with an angular acceleration of 30 radians per second squared. So alpha is equal to 30 radians per second squared. And let's just need to correct this because this is omega initial, and now this is omega final. Or excuse me, this is omega initial, and then it goes down to 0. You turn it on, it reaches a speed of 240 radians per second. Then you turn it off, and it begins slowing with this angular acceleration. Now, I also need to be careful about my signs. What is the sign of these two, the omega naught and the alpha? It's slowing down, so the velocity and the acceleration are opposite directions. You have to make that leap at some point during the exam, I'm pretty sure. That means that this has to be negative. Because it's slowing down, omega and alpha are opposite directions. And now I want to know the angular distance. Now look, I know omega naught, and alpha, so I can find t, and I need t in order to find theta. So this is a 2-step problem. First, I have to find t, and then second, I can find the angular distance, theta. So first I'm going to say omega, that's 0, equals 240 minus 30 times t, so t is equal to 8 seconds. It takes 8 seconds for this thing to stop. And then theta is equal to 240 times 8 minus 1/2, plus 1/2 of negative 30 times 8 squared. Do you know what the answer is right off? Huh? D? Okay, yeah, 960. Okay, 960 radians. That one's kind of worded a little funky. I wouldn't word it that way. This was, what year was this? 2020? But you'll definitely have a kinematics problem that is similar to this. It might even require 2 steps. But when you get it, don't freak out. Just write down what you know. Write the equations. In fact, you'll have the equations. So just write them again. You have time. Just write them on your exam. And then go through and look at the variables. If it says speed, that's omega. And then ask yourself, is that an initial speed or a final speed? And if it says acceleration, that's alpha. And then ask yourself, is it positive or negative? That's kind of important on all the parts of this exam, actually, that you're asking that question. Is it positive or is it negative? It's true for the momentum questions, too. Okay, Emily? No, it's okay. It's fine. It's all right. Emily?
Why isn't omega not a 0 here? Because it's originally off.
Yeah, so that's what I said about the wording being kind of funky. That it switched on. Initially, it was off, and it wasn't moving. Then you turned it on, and it sped up because it's 240 radians per second. Then you turn it off. And so fan, it starts to slow down. So I start at 240, I slow down, and then I go to 0. So I had an initial time when it was speeding up, but that's not the time that I'm asking the question about. That's sort of just, I don't even know why I put that. That's kind of relevant. Okay? I said, yes, kinematics questions. I think there are a couple actually. All right. What else, y'all? Noah?
On fall 21, exam 3, 14 and 16.
Fall 21. (14 and 16). Which of these statements are true for elastic collisions? Yeah. All right, so let's think. Elastic collisions, I like to think of them elastic, meaning they're like really, really bouncy. The things bounce off of one another really well. And when something's really, really bouncy, it doesn't lose any energy, right? Think of like a really bouncy basketball. If you drop it, it goes down, and it comes up pretty much where you dropped it from. Elastic conserves energy because it's really, really bouncy. And so an elastic collision, energy is conserved, and in all collisions, momentum is conserved. That's why conservation of momentum is so powerful, because it's true in every situation. Anytime you bump into something, momentum is conserved. And so if those two are true, then 3 and 4 are not true. I mean, those are opposite of 1 and 2. Momentum is conserved, or momentum is not conserved. Energy is conserved, or energy is lost. So what we lose it is opposite being conserved. So 1 and 2, which is B, or no, C, excuse me, C is the right answer. When you get those, just go through each one, because like if I know that 1 is correct, then that gets rid of that one. And also, by the way, gets rid of, well, no, just that one. But anyway, go through and, you can select the options by picking what you know for certain is true. Now, you said another one, right?
16.
16. Impulse is just a fancy word for change in momentum. And so when I say delta P, I just want to know what is the change in momentum, and that's going to be M times delta V. This is not explicitly on your equation sheet, but it does say that P is equal to mv. And so impulse, which is the change in momentum, is just M times that delta V. So this is VI, this is VF, this is going to be M times VF minus VI. That's 2 times 3 minus negative 4. 2, excuse me. 3 minus negative 4. That's 2 times 7, or 14. Be careful with your signs here. And I give you the signs explicitly, but as I said before, if I have two velocities that are opposite directions, that means that the delta V is actually going to be the sum of those two numbers. Okay? Because it's a bouncing situation, a recoil or a rebounding. So it would be 3 minus negative 4, which is 7. Notice that if I just said 3 minus 4, I would have gotten 2, which is also an option. So when you get to one of these problems where you have to find the impulse or the change in momentum, just watch your signs really, really closely. All right, what else, y'all? Allie?
12 and 18, again,
19?
2019.
Sure. Oh, that's the wrong direction. All right, this is 2019, number 12. Okay, this is another impulse problem. Oh, number 12, I'm sorry, not 10. You have a particle of mass m, and you increase its energy by a factor of 3. What has happened to the object's momentum? We did one of these in class. It was similar. This was a little more difficult than the one we did in class. Let me show you. the momentum is equal to m times v. The energy, the kinetic energy, is equal to 1/2 mv squared. I say I increase its energy by a factor of 3. That means this increases by a factor of 3. So what must I have done to V in order to increase the energy by a factor of 3? Well, what squared is equal to 3? Root 3, right? Similar to that question you asked about earlier. So this would be root 3. Now if I consider my momentum, my speed has increased by a factor of root 3. That means my momentum is also increased by a factor of root 3. Those are a little more difficult. You just don't normally think of increasing something by the root of a number. Okay, all right. I'm pretty sure there's one like that. I think I told you all that in class, right? Just this asking if the kinetic or the momentum changes by a certain amount, how does it affect the other? Did I tell you all that in class? I don't remember. I'm not seeing it right off, but it doesn't mean it's not on there. All right. What else, y'all? Emily?
I don't really know, like, pinpoint question that you can use.
Yeah. So I think the question is, yeah, we have some various accelerations that are floating around. We have the centripetal acceleration. We have another acceleration that's just our tangential acceleration. I'm going to give it a subscript. We don't always put a subscript like on this. And then the other acceleration that we have is our angular acceleration. If I have an object that's rotating with an angular acceleration, that is, it's like a disk or something that's speeding up, like it's rotating faster and faster and faster, then that means that any point on that disk has also a tangential acceleration. You can imagine that it's like a point that's traveling in a straight line and it's speeding up. And if this thing is rotating faster and faster and faster, that means that the tangential, then it also has a tangential acceleration. Now that tangential acceleration, if you recall, is equal to alpha times r. We don't usually use that very much, but sometimes I'll ask explicitly, what is the tangential acceleration? And it's just alpha times r, the angular times the radius. There's the centripetal acceleration too. If I imagine an object with a constant angular velocity, that is that alpha is equal to 0, a wheel or a disk or whatever it is that's just spinning at a constant rate, any point on this disk is going to have a velocity that's constant, but it's going to be changing direction all the time. And because the velocity is changing direction, it has a constant speed, but the direction of that velocity is changing at every moment. Because of that, it has a centripetal acceleration. And that centripetal acceleration, let's say the centripetal acceleration describes how the velocity changes direction. So the centripetal acceleration is equal to that v squared over r omega squared r. Okay? And then finally we have the angular acceleration, and that just describes, if this thing is changing, if omega is increasing or decreasing, it's, by what rate is it increasing? And the units for that are going to be in radians per second squared, or revolutions per second squared, or degrees per second squared. These, by the way, are going to be in meters per second squared, both of these will be in meters per second squared. I think you also asked, like, how do I know when to use radians or revolutions? Anytime you're calculating a centripetal force, it must be in radians. Must be. If you're doing kinematic stuff, it doesn't really matter if it's in radians or revolutions. The good news is for you is that there is no problem where it matters. That you're just going to use the units that you're given. Okay? That's not true on every exam that I've given. In the past, I've given some problems where you have to change the units. But unless I explicitly say, express this in such and such units, which I might do that, but unless I explicitly say, ask that, then you don't need to worry about changing the units. Is that clear? That's not new. I said that in class, I'm pretty sure. Did I say it in class? Yes. Okay. All right, Joe. Other questions? Any just particular topics that we've sort of dealt with a lot of details, but any particular topics that would be conservation of energy, work and energy, like where if I do work on an object, I change its energy. Rotational kinematics, we've done some of those problems. That's really just using those two equations. Excuse me, centripetal forces, like the girl with the yo-yo, like that you're going to see in your free response, are, okay, 2019, 14, exam 3, right? This one, the Ferris wheel? Yeah. So this is a lot like your free response. So it's probably a good one to look at because it'll help you to understand the free response a little better. The only different thing about this one from the free response is in the free response, your centripetal force is the tension, but in this case, the centripetal force is the normal force, or some combination of the weight and the normal force. So very similar. I'm just going to write down sort of what I know. I know the radius, I know omega, I know mass, and I have this Ferris wheel. You all know what a Ferris wheel is, right? Like a big wheel that moves around. And at the top, I have two forces acting. I have the weight acting in that direction, and I have the normal force acting in that direction. So just like you'll do for your free response, I just say the sum of the forces in the y direction are Fn minus Fw, and that those are equal to the mass times the centripetal acceleration. Now, the centripetal acceleration is in the downward direction. So I'm just going to put a little negative right here just to remind me that that is a negative value. The centripetal acceleration is always towards the center of the circle. Okay, so that's how I determine if it's positive or negative. If it were at the bottom of the Ferris wheel, the centripetal acceleration would be pointed upward. Likewise, the normal, well, this would be the same, but the centripetal acceleration would be pointed up. You'll see the normal force would still be up and the weight would still be down, but the centripetal acceleration would be in the upward direction. All right, so I want to know the normal force. I just say the normal force is equal to the weight minus MAC. The weight is a 100 kilogram person, 100 kilograms times 10 minus 100 times AC. I need to figure out what AC is. AC is equal to omega squared R. That is 0.2 squared times the radius, which is 30. What is that? Yeah, 1.2. So this is equal to 1.2. And so that's 1,000 minus 120, or 880 is the answer. Notice how this would be different if I were on the bottom. Then if I were on the bottom, it would be a little bit different. I'd have my normal force up. I'd have my weight still down, but my acceleration would now be in that direction. So the only difference that we would have is that this would become positive, this would become positive, and that would become positive, and then the answer would be 1120. Y'all see how that works differently? It's very similar to your free response, except you're now dealing with the normal force of the weight instead of the tension weight. We just think what I said, that if I was on the bottom of the Ferris wheel, now the centrifugal acceleration is pointed upward. So whereas this was a negative value before, now it's a positive value because it's going up. Down is negative, up is positive. Okay, are you good? Sure. Okay, it's a good question. You're not going to see it on the multiple choice, but like I said, understanding that question will help you to understand the free response better. And I get it. Y'all can just memorize the free response, and some level that'll be okay. But you'll understand the multiple choice better if you actually understand the free response. If you don't kind of not just having memorized it, I mean, it's difficult to do that here because you don't know what numbers are. But if you understand it, you'll be better off. Okay. What else? Jude?
Okay, I hate to ask, but could you do a problem if it's involving like, I'm sorry, if that has a power at an angle? I'm not sure if I'll have anything like that.
Yeah, I think I know what you're talking about. With the clock, you mean?
Not a clock, like involving like power.
Oh, power.
I'm not sure if I have anything like that.
At an angle?
Yeah, like, preferably.
Like this one right here? Where I'm doing work done
Yeah.
a certain force when it's at an angle. Yeah, so this, Jude's not in our class, but, he's in the 201. But this is a problem that you might have too. Probably will, actually. What is the work done by the force? Now remember that work is equal to FD cosine theta, right? Where theta is the angle between the force and the displacement. And I want to know the work done by the force F. That's this force right here. So notice here, there's the force. The displacement is in that direction, and so the angle is 30 degrees. So the work then is equal to the magnitude of the force, the magnitude of the displacement, 4 newtons, 2 meters, times the cosine of the angle between them, cosine of 30 degrees. So that's 8 cosine of 30, which is about 6.9 or 7, 6.9 joules. You will definitely have one like this. Hopefully, well, the other question that I could ask is not just what is the work done by this force, but what is the total work being done by all the forces. Now I know that this force does no work because there's no displacement in that direction. Likewise, this force does no work. This force is going to do what? Positive or negative work? Negative work. So I could ask you what is the total work being done, and the total work being done would be 6.9 joules minus this force, 2 newtons, times the displacement over which it acts is also 2 meters, and so that would be 6.9 minus 4, 2.9 joules. Those are two possible problems. This question was asking the work done by that particular force, but I could also ask what is the force done, or the work done by the total amount of work. I could even ask you, what is the speed of this thing? So now that I know that I have 2.9 joules, I've done a total of 2.9 joules of work, I would just set it equal to 1/2 mv squared. Because that's the kinetic energy that it's going to have after it goes through this 2 meters of displacement of those forces acting on it. And then I could solve that for V. I don't have the mass here, so it's more difficult. Well, no, I have the mass. It's 1 kilogram. I could solve that for V. I got that mass of 1 kilogram. Because the weight is 10, right? And so 1 times 10 is 10. Also notice here that this is 10 newtons and this is 8 newtons. You might be wondering how that came about. But remember, this force has a component that's in the y direction. And that y component is 2 newtons. All righty? Other questions? All right, why don't we stop there? But if you have more questions, you can stay after, we can talk.